Hello viewers, welcome to EF. Today is the 13th video of complexity theory. In this video I would like to discuss about some example of reducibility, and then I would like to say the theorem we get after the reducibility and what is transitivity. So let's see. Question is, give some example of reducibility. We know that the traveling salesman problem TSP that can be polynomially reducible to TSPD, means traveling salesman decision problem. Next we can do TSPD, which can be polynomially reducible to TSP, and then there is one very important problem, that is the first NP complete problem said by Cooks. So that is set satisfiability, and we can polynomially reducible set to 3 set. We can also polynomially reducible 3 set to set, and then set 3 set can be also polynomially reducible to vertex cover problem. Now these are the problem which are called left side and right side. These problems are proving NP complete problem because this is fulfilling the second part of NP complete problem. By this reduction we can prove these problems are NP complete problem. By this 5 proof we can say that TSPD, TSP, 3 set and vertex covers are NP complete problem. We will see these proofs later. So for this video we will see some related problem of P and NP. So now let's see what is the theorem we will get after reducibility definition. There is a theorem that if we can prove L1 and L2 for two language, L1 is if L1 is polynomially reducible to L2, implies that I can solve L2 in deterministic Turing machine in polynomial time, then I can also solve L1 in polynomial time by a deterministic Turing machine. In that case, we can say that L2 is in class P, then L1 is also in class P. For two languages, L1 and L2, such that L1 is a subset of sigma 1 star, where sigma 1 star is an input of Turing machine, and L2 is a subset of sigma 2 star, where we get this sigma 2 star from this another deterministic Turing machine, and we from M2. We have seen this in my last video. Now if the situation is like that, then we get two situations. First, if L1 is polynomially reducible to L2, then L2 belongs to P, implies that L1 is also in P. Means if I can solve L2 in polynomial time, then I can also solve L1 in polynomial time. Now similarly, if L1 is polynomially reducible to L2, then if I cannot solve P or solve L1 in polynomial time, then I am also not able to solve L2 in polynomial time. For the brief proof, you can check the book of Carey and Johnson. And I will move to the next question. What is transitivity? Explain. We have three languages, L1, L2 and L3. L1 is a subset of sigma 1 star. L2 is a subset of sigma 2 star, and L3 is a subset of sigma 3 stars. Here sigmas are the inputs from different Turing machines. Now if we can prove that L1 is polynomially reducible to L2 and L2 is polynomially reducible to L3, we can also say L1 is polynomially reducible to L3. That is called the transitivity. For the proof, I will discuss later, but not in this video. So let's see what is the hard part of NP complete. This is very important and interesting problem. First, let's consider a set which contain the decidable decision problem. Now in this set we have a set called class NP problem, means the problems which are in class NP that can be decided by a non-deterministic Turing machine in polynomial time. Now we have also a subset which is class P, which can be solved by deterministic Turing machine in polynomial time. And we have also this NP complete problem, which are in NP class, and other NP class problems which can be solved from this problem. I already explained once the NP complete problem, but again I am telling that the NP complete problems are the hardest problem in NP class, because the reason I will tell. First, let's see the NP complete definition once again. We know that a problem L is called NP complete if it belongs to, if it is a subset of sigma star, and then if it is belongs to in NP, and for all other problems which are in NP class, like L prime, we have L prime is polynomially reducible to L, then it is, this L is called NP complete problem. Now we also have another theorem that says like this NP complete problem, if we have, and this, if this NP complete problem is in class P, then we have a situation like, okay, if there is at least one program in class P that is NP complete, then we can prove that P is equals to NP. And we can also prove that, okay, if that program, or if that problem L that is NP complete is does not belongs to class P, then all NP complete problems L prime is not belongs to P class. Hence it means that P is not equals to NP. We have another definition, what is called NP hard. This is the most interesting part, and where we know that TSP is NP hard problem. It does not have any algorithm for solving in polynomial time, and if we can solve this kind of problem, there is no more encryption, all encryption can be decrypted. So let's see what is NP hard problem. A problem is NP hard. Let's say P is a problem which is NP hard if we have other problem L that belongs to NP, and L is reducible to this P class, and P itself cannot be decided by an algorithm. That is, all problems which are in NP class L can be polynomially reducible to P, but P itself has no algorithm, then it is called NP hardness or NP hard. So what is the difference between NP complete and NP hard? It's very easy to say, but it's actually a difficult problem. We can research on it. So if there is an algorithm for P problem, then it is called NP complete, and P is in NP and also NP complete. If there is no algorithm for P, then it is NP hard, and P is not in NP, hence not in NP complete. So that's all for in this video. In next video I will prove deeply, does it P is equals to NP or P is not equals to NP. Thank you for watching this video.